Sadly, we did not get to combustion analysis in lecture, but you are going to have to do combustion analysis problems on ALEX, and it's also actually fairly cool and useful in the lab as a way to find out what a sample is made of. Combustion analysis is conducted in an apparatus where you have a sample. The sample is usually composed of carbon, hydrogen, and oxygen. Sometimes oxygen, sometimes not. You burn this sample in the presence of unlimited oxygen gas. And when you burn it, like any combustion reaction, you get the products of water and carbon dioxide. Since this is all contained in this apparatus, you can actually do a quantitative analysis on the amounts of water and carbon dioxide that you obtain from this reaction. This allows you to analyze any organic compound that is made of carbon, hydrogen, possibly oxygen, by simply burning it up and figuring out what the products are and how much of them you have. This generation of carbon dioxide and water can actually lead you back to the empirical formula of this sample. Imagine you're a chemist and you have some compound and you want to know what its formula is. This is a way to achieve that. You can get the empirical formula. Additionally, if you know the molar mass of your compound, you can also derive the molecular formula, just like you've done previously in this course. We're going to tackle a problem head-on, kind of a fun one, I think, because it involves vanillin, which is a lovely compound. It is a flavoring agent, as I'm sure you know. It has a really pleasant smell, and it just so happens it's made up of carbon, hydrogen, and oxygen, so perfect for our combustion analysis problem. We're going to say that we have a sample of vanillin weighing 2.5 grams, and after we burn it in the type of apparatus that you just saw, 5.79 grams of carbon dioxide and 1.1 grams of H2O were obtained. The end game here is to figure out the empirical formula of vanillin. Now you might be saying, well, I can just look that up. But that's not what we're going to do here. We're going to deduce it, just like good Sherlock Holmes chemists. Here's our problem again. And as with any problem, you have to pay careful attention to the data that you're given. 2.5 grams of our sample, 5.79 grams of carbon dioxide obtained, and 1.1 grams of water obtained. You can imagine that in that situation, we don't know the formula of our sample. But in this case, we're actually told it has carbon, hydrogen, and oxygen in it. And we know that there must be some subscripts, X, Y, and Z, that apply to the different elements. Other than that, we know we're going to burn it in oxygen and we're going to produce carbon dioxide and water. So this is a potential, not balanced, but let's call it a skeleton equation for what's going on here. We're going to make a few necessary assumptions about this process. One is that all the carbon in the product CO2 originates from the sample, and all the hydrogen in the product H2O also originates from the sample. What do I mean by that? I mean, when this sample decomposes, when it burns in oxygen, all the carbon in it goes to the carbon dioxide, and all the hydrogen in it goes to the water. Let's consider oxygen now. The oxygen in the products can come from either the sample or the oxygen gas in which the sample was burned. In other words, we have oxygen in our sample, we have it in the oxygen gas, and we have it in both of our products. we don't necessarily know if the oxygen in this compound is accounting for all the oxygen here, or if the oxygen in which it was burned is accounting for all the oxygen here, or if it's some combination, which is the most likely. So we have a little problem here. We have a computation problem, since we don't really know the origin of the oxygen in the products. But we have a clever way to tackle that, so stay tuned. That clever way, which we're going to put into action with our vanillin problem, is that we can find the grams of oxygen by subtracting grams of carbon and hydrogen from the mass of the sample that we burned. This is going to make more sense when we put it to work in the problem. So let's look at an outline of the steps, which are many, that we need to do for this problem. The first thing we do is we take the 5.79 grams of carbon dioxide, convert into moles of CO2, then go to moles of carbon and grams of carbon. After that, we take our 1.18 grams of H2O, convert that into moles of water, and then moles of hydrogen. Notice the 2-to-1 ratio here, 2 moles of hydrogen for every 1 mole of water, and then convert that into grams of hydrogen. Finally, we calculate the grams of oxygen, again, by taking grams of our sample and subtracting grams of carbon and grams of hydrogen. By definition, if our sample is made of carbon and hydrogen and oxygen, if we subtract grams of carbon and hydrogen from our sample, the only thing that can be left is oxygen. Finally, we're going to convert our grams of oxygen, if any, into moles of oxygen. I said finally, but that's not exactly true. What do we have so far? We know moles of carbon, we know moles of hydrogen, and we know moles of oxygen. That allows us to develop an empirical formula for this problem. How do we do that? Like you've always done. We take the ratio of moles of carbon to moles of hydrogen to moles of oxygen. We perform the usual manipulations to get whole numbers, and then we have an empirical formula. If the problem asks, you may have to find the molecular formula using the molar mass provided in the problem. As you know, the molecular formula is always going to be some whole number, multiple of the empirical formula. The way I've set this up is so that you can try to answer each step of this problem, each important step of this problem. So I've set it up as a multiple choice. And that way you can break it down into steps. And you can, at the end, I will give you the answers. You will see if you are correct for each of these discrete steps. The first thing we have to do, as noted when I outlined the procedure, is we have to figure out how many moles of carbon dioxide, moles of carbon, grams of carbon, and then rinse and repeat for moles of water, moles of hydrogen, and grams of hydrogen. For this first step, I just want you to figure out how many moles of carbon and hydrogen there are in each of these gram amounts for carbon dioxide and water, our reactants. And of course, you know how to do this. So you can give it a stab. I'm going to remind you one more time that there are 2 moles of hydrogen for every 1 mole of water. For carbon, it's simpler. It's a 1-to-1 ratio. So pause the video, see if you can get the right answer here, which, as I say, will all be revealed going forward. Okay, if you got that problem right, you would have found that you have almost equivalent moles of carbon and hydrogen. So we're on our way towards getting an empirical formula, but our mystery character is still oxygen, and oxygen is a little tricky. So The next step that I'm going to ask you to perform here is to figure out how many grams of oxygen there are, if any. We know there are in this case because we were told so in the problem, are in your 2.5 gram sample of vanillin. In order to get there, you're going to have to take the mole amounts here and convert them to gram amounts here. Then, as you hopefully recall, after you have your grams of carbon and hydrogen, you're simply going to subtract them from the sample mass, which is 2.5 grams. Try your luck, pause the video here, and see what you get out of these possible answers. Next up, we want to know what the empirical formula of vanillin is. We have our moles of carbon and hydrogen. If you did the last problem correctly, you would have figured out that you have 0.788 grams of oxygen in your sample of vanillin. That you can easily convert to moles using the molar mass of oxygen. And then you will have moles of all three, carbon, hydrogen, and oxygen. From there, you can work your way towards the empirical formula. It'll take a little mathematical manipulation, but you can do it. Pause the video, give it a try. Okay, so that was a lot of work. And yet, if you're really efficient, I managed to cram the entire calculation into the bottom half of this slide here. So let's break it down. And it's all in the table here, of course, as well, or most of it. But here are the actual calculations below. So converted grams of CO2 to moles of CO2 to moles of carbon. I'm going to need that, so I write it down here. Then I do another calculation to get to grams of carbon. Repeat that for water. Go from grams of water to moles of hydrogen. Write down the moles of hydrogen. Get the mass amount of hydrogen in grams. Then use these gram amounts to subtract from the original mass of the sample. Get your gram amount of oxygen and use the molar mass to find out how many moles of oxygen. Now you can use these three numbers to get at your empirical formula. It's a ratio that you see here, carbon to hydrogen to oxygen. What do? We divide each of these subscripts by the smallest number, and that gives us C 2.66, H 2.66, O. Not good enough. We need whole numbers. After some trial and error, you will find that if you multiply by 3, you will get C8H8O3, and you're done for the empirical formula. This problem doesn't ask you to do the molar mass. See how easy that was? I know, a lot of steps, but doable. Practice makes perfect.